This time we're going to be covering section 5.6, which is the definite integral as a limit sum. So we're going to approximate the area using rectangles, using the left endpoints, the right endpoints, or the midpoints of each of these rectangles. And then we're going to look at the definite integral as a limit sum. So let's take a step back and see what we're doing here. So the ideas in the previous sections, what we have said is the definite integral represents the area beneath the curve in between the x-axis and the curve as long as it's positive. We've also found the area between two curves. So why is the definite integral representing area? And that comes from really the definition of integration, which is what we learn here. So what we're going to do is if we wanted to find area previous to this class, what we'd have to do is use those geometric shapes we know. Rectangles, circles, triangles, any of the shapes that we learned in geometry. And we would have to actually estimate the area by finding the area of several different rectangles. This topic in business calculus and brief calculus is not near as important as it is in regular calculus. In a regular calculus, they go up, and this idea of breaking things into smaller pieces and adding up smaller pieces is a very, very important concept that you'll see. So let's see what I expect you guys to be able to do out of this section, which is essentially, can you estimate the area beneath the curve using rectangles? The examples in the book aren't too nice. I try to put some nicer examples in here that aren't in the textbook. I tried to make my own pictures here to make it easier for you. So let's take a look. So the first thing says approximation of area. It says consider the region bounded by the y-axis and the curve of f of x equals negative x squared plus 25 on the interval from negative 1 to 5 as shown in the following figure. So that is the graph of negative x squared plus 25 on the interval negative 1 to 5. It says we wish to approximate the area of the shaded region. To do this, we will use shapes that we know as areas, such as rectangles. So if we use multiple rectangles, we can get close to the area of this. And so what are we doing here? If you take a look at what we're doing, we have 1, 2, 3, 4, 5, it looks like 6 different rectangles. And you'll see in some of the areas we actually missed the area. We're underestimating, but in part of the area we're overestimating. So what's the idea is if I use these rectangles, it would be an approximation of the actual area, not exact. We know the definite integral is exact, but this is how we came to the definite integral. Okay, so it says to estimate the area in the bounded regions, we would determine the area of each rectangle and then add up these areas. So what are we going to do? Well, the first thing you need to do is consider the region, the interval that you want to find the area on. So on this one, it was from negative 1 to 5. So that number we're going to call n, the letter n. N is the number of rectangles you want, right? And then one thing we're going to do to make it easier for us is we're going to make the width of every single rectangle the same. Let me say that again because it's very important. We're going to make the width of every single rectangle the same. So what are we going to make the width? Well, we're going to call it delta x. And all we're going to do is take the length of the interval, which would be b minus a, if your endpoints are a and b. B minus a would be the length of the interval, and then divide it by the number of rectangles you have. So for instance, on this one, we had an a value of negative 1, a b value of 5, and it seems we wanted 6 rectangles. So if we did 5 minus negative 1, that would be 6, divided by the number of rectangles, which is 6, would give us a width of each rectangle of being 1. And if you notice on the picture, if you look, every single one of those rectangles does have width 1. So delta x is just the width of the rectangle. Every one of them is the same. So all you have to do is subtract the endpoints, the right endpoint minus the left endpoint, divided by the number of rectangles. Okay, the next thing you want to do is just draw that interval from A to B and break it into those rectangles so it can help you visualize what numbers are you going to be plugging in. It says determine the label of each endpoint. You should start with A and increase by delta x each time. I'll show you what that means through these intervals, but essentially all it is saying here you're starting at negative 1. we decided that the width was 1 every single time. So if we started at -1, the next one should be 0, 1, 2, 3, 4, and 5. That's where we would be breaking up our rectangles, is you start at the left endpoint A, and you just add whatever delta x is each time. On the problems that I do, it's a little more natural to do this, but I'll show you what it looks like, okay? It says circle the endpoints that you wish to use. We're going to be plugging in left endpoints, right endpoints, or midpoints, which I'll show you shortly. Then it says determine the height. And how do you find the height of a rectangle? Well, the height of the rectangle, for any rectangle, is that function value. So all you're going to do is take whatever that x value is and plug it into that interval, or sorry, into the function to find out what the height of the rectangle is. So remember, if you're trying to find the area of a rectangle, you need height and width. So to find the height, we plug it into the function. To find the width, we already found the width. That's b minus a over n. A nice thing is that the width is going to be the same every single time. Okay, so it says determine the area of each rectangle by multiplying its height by its width. Again, the height is found by plugging the endpoint into the function. The width is found earlier. And then you're going to determine the total area by adding all of the areas of each rectangle. So we're going to find the area of each rectangle, and then we're going to add them all together. Okay?